I'm and I'm going to be talking about Multicore for Mortals, getting your Perl programs to take advantage of multiple CPUs using Unix processors. So this talk is mainly a case study of how I set up one program using for. I'm not trying to give you a silver bullet for concurrency. I'm not trying to advance the state of the art in parallel programming. And in particular, the techniques I'm talking about won't necessarily work in all situations, but they are techniques that you can use right now to work on any old Unix system in Perl 5. So until a couple of months ago, I worked for Register, and we generated a lot of log files from our web servers, and some of my work involved doing analysis of those files. So I wrote a program called LogTool to help me with all that sort of thing. It's kind of a Swiss Army knife for log processing. It knows about the file format that you use for log files to read, knows where those files are stored, and you can select what files you want to look at, what dates they're from, which subset of requests you're interested in, what sort of answer you want. For example, you can count impressions, you can count distinct field combinations, you can take the sum of the numeric field, or the mean and the standard deviation of the numeric field, and for any of these sorts of analysis, you can break that down by some other set of fields. It's deliberately a programmable tool. It's kind of a bit like doing SQL queries on a database table that's got all the log file, log lines in it, but without ever actually having to use the database. And it's always been pretty fast because it relies on underlying in-house log filing code that we've been working on and using and profiling for a long time, several years. But of course, these things are never fast enough. And that's especially true when you're trying to analyze large amounts of data. And we read just the genuine requests, just the page requests, we're talking about 20 gigabytes or more of data per month. But it did occur to me late last year that the problem is actually embarrassingly parallel. And this is the point at which we just upgraded all our servers to 8 cores. So I started thinking about what we need to do to parallelize it. So just to give you some idea of where I actually got to in the end, this is a graph of the speed of I got. So this is a particular test I ran, which is meant to be representative of the sort of work you usually do. So this was counting impressions and unique users over a month's worth of log data. And it's all running on the same machine, which had 8 cores and 16 gigs of RAM and plenty of fast disk. And for each test, I was careful to make sure that the input data was in the kernel's I/O cache to eliminate the sorts of variability. So the horizontal axis here shows the degree of parallelization used for each run, from 1 upwards. And the vertical axis shows the relative speed up we got to that run. So of course, for one process, that's a relative speed up of 1 compared to sequential execution by definition. And you can see that for small amounts of parallelism, the speed up is almost a straight line. It's the steep line on the left. And that tops out a factor of just over 6. And then increasing the parallelism still further produces additional performance improvements until we get up to, in this case, it was 64 processes, where we have a speed up of just about 7.2. So 8 cores, speed up factor of 7.2. That means that we've got a nearly linear speed up in the number of cores on this machine. So how do we do this? Well, this is the bare bones guts of the top level of what LogTool does. It creates this aggregator object. This is the thing that actually does the analysis. And it finds the list of log files to analyze. And each time it finds a file, it processes it, and that just involves taking each line one at a time and feeding it to this aggregator object. And when we've done all the files, we ask the aggregator to emit a report of what we found. So the basic idea for parallelizing it went like this. Suppose we want 8 workers. Then the easiest thing to do is to have each one of them process 1/8 of the files. They're going to gather data they found in the log files, feed it back to the master, and then the master aggregates everything it found from each of the workers and emits the report as before. So with that kind of vague model in mind, the next question is, how do we actually decide, and what do we actually use for parallelism, for doing these independent workers? And the two options are threads and processes. Now, I should admit that I have kind of a prejudice against threads, especially conventional shared memory threads. They always seem to me to be pretty hard to get right, and often quite hard to make fast unless you're really careful about the way you use your blocking. Now, admittedly, Perl's threads are pretty different. For one thing, you don't get sharing by default. You have to ask for sharing in specific places you want it. So you don't need to worry as much about blocking. But the cost of that is that all the unshared data is copied whenever you start a thread, and that can be quite slow. So the alternative is processes as created by Unix fork. And this way I find that a lot of the issues go away. There's no shared memory, so you can't accidentally scribble on memory that someone else is reading from at the same time. They're cheap to create. You rely on the operating system kernel to do all the heavy lifting, and all it has to do is set up some page tables, and it gives you what looks like a copy of the entire process, but it hasn't actually had to copy any data at that point. Now, the problem with fork, of course, is you don't get a shared memory, and that does mean that communication can be a little slower than it might be for threads. Threads will probably give you maximum throughput if you want it. But then, if you wanted the absolute maximum throughput, well, you probably weren't going to be writing in a high-level language like Perl, so that doesn't seem terrible to me. Instead, you use files or pipes or network sockets, or something like that, to communicate between your processes. And that's perhaps a good thing. It means that the programming approach you use is necessarily more similar to what you get if you were trying to make your program run on multiple independent machines rather than on multiple cores within a single machine. So, having decided to go with forked processes rather than threads, the next step is to actually make the code do what I want. So this is the structure we started with, the code I showed you before. And we want to change this essentially in three ways. We've got to create the worker processes, we've got to collect their data when they finish, and we've got to be able to extend these aggregators to be able to save and merge their data. So let's start by seeing what happens when we add the code to create worker processes. And you should be able to see that most of the code is still there, that's the black bits. And the functions being called, they also haven't changed at all. But all we've done is we've broken it up a bit, we've moved the loop over files itself into a loop over creating processes. So I decided that each worker process would save its state to a temporary file. It's very simple. So we'll create a hash, that's my send worker output FH, and that's going to map from a worker process ID to the temporary file it's going to write to. Then we'll divide the log files up into a list of subsets, as many as there are worker processes. And then we'll for one process for each subset in the loop. And the master process, all it has to do at this stage is record the file handle and the process ID in the hash. Meanwhile, the worker is running in the background, and it starts processing its subset of the original files. So when the worker has then finished processing those files, it saves its state to the temporary file, and then exits. So that's creating the processes. The next step is just to get the master to wait for all the workers to finish and to collect the data from them. So once the master has started all its workers, it just loops calling Perl's wait built-in. What wait does is it pauses execution of the process until at least one of the child processes to that process has exited. And wait returns the process ID of the child it found that has exited, and it stores its status in $?. So the master just does a couple of quick sanity checks to make sure that everything is what we expect it to be. And then it reads the data from this worker's temporary file and merges it into its own copy of the aggregator object. And of course, once it's done that for all the worker processes, it just emits the report as before. Now, it might look a bit surprising that we've only created one aggregator, and how can these all be independent? But that's, of course, because we've got the master and the workers are all running in separate address spaces. So each time the master forks a new process, the worker gets effectively a virtual copy of the aggregator. So there is actually one aggregator object per process, even though we only create it once. So the last remaining task is to save and merge data from the aggregators. So let's start by looking at what the aggregator classes look like. And we have one aggregator class for each type of analysis that the log tool can do. And in the sequential version, the guts of each one look like this. There's an accumulate method. Every time the main program meets a log line, it feeds the data extracted from that line to the accumulate method. And then when it's generating the report, it tells the aggregator to aggregate the data it's seen. In this case, for just counting impressions, neither the accumulate nor the aggregate stats are actually very interesting, but this should be enough to give you an idea of what we need to do. So, with the parallel version, we want to extend each aggregator class with the ability to save its data to a file, and so that workers can tell the master what they've seen, and to merge data from a file into whatever they've already got. And that just requires two more methods for each one. So for each aggregator, we ended up with these two methods, state and merge. State just returns an arbitrary Perl data structure. In this case, it's a hash graph containing counts. And the merge takes one of those data structures and reads all the data from it and puts it into itself. So in this case, again, there's not very much going on because count is simple, but you should be able to see what happens. You might also spot that there's no code here which actually deals with saving data to files or reading data from files or anything like that. I decided to leave that part of the job to the caller, so that each aggregator class only has to worry about what data needs to be saved and how to merge it once you've saved it and reloaded it. So this is kind of a separation of concerns thing. We get the actual file handling out into somewhere else. But that code does turn out to be straightforward too. I'm using Storable to do the heavy lifting. I like to look at it. It's fast, it's easy to use, it ships with Perl, which is always very convenient, but it would be easy enough to use anything else alternatively, JSON access, any of a variety of data serialization modules. And of course, the routines I've actually got are just trivial wrappers around storable routines that serialize to and from a file handler. There's only one real subtlety. When the worker has finished writing its data, it advances the file offset, the temporary file, to the end. But the file handler we've got is shared between the worker and the master, and there's only one file offset between all shared copies of the file handle. So when the worker has advanced the file offset, well, the master's version gets advanced as well. So before we actually read the data from the file handle and the master, we need to rewind the file back to the beginning, and that's what the sequence is doing. So it turns out that's actually pretty much it for the code. We needed to extend each of the individual aggregator classes with state and merge methods. That was just a small matter of programming. So going back to the performance graph, the numbers across the bottom needs to be the number of processes we forked. I'm blind slightly there. It's actually half as many processes as we forked. It turns out that in practice, all the logs are stored compressed on disk, and we have an extra process to do the uncompression transparently when we read from the file. But again, you can see that for a small number of processes, we get this very, very clear linear speed up, and we eke out just a little more by increasing the number of processes even further. And I was quite surprised that 64 processes on an 8-core box was still a performance improvement, but, well, it was, and I was pretty happy with that. This is the speed of the 7.2, it's a near linear speed up for 8 cores, and this only took an evening's work to put together. It was just a little side project I had in mind to do with, and